So let's solve this. This is CMI 2023 Part B, problem number 5. Let's see what it's asking. So it's asking. It's a very simple statement. It's asking you to find the determinant of the following 5 cross 5 matrix. You all, of course, know, all of you, the definition of a determinant of a matrix, and the matrix is given, right? Now, you already know an algorithm. There is a well-known algorithm to find the determinant by using this and then calculate the determinant of this. But this is a 5 cross 5 matrix that can take a bit of time, right? So I believe the best possible way, the best possible mentality to solve a problem in a CMI or ISI type forum or entrances is to keep in mind that how to solve rather in all the entrance examination, because this is time bound. So to solve every problem, there is a easier way out, you know, and it's more interesting because it's a subjective problem. So step number one is to first of all know the information of the problem. The step number two is to always think about the simplest possible way to solve a problem. Now, the question is to find the simplest possible way to solve this problem. Okay, this is the whole idea. Now, how to think about it. So therefore, the question boils down to answering what is the simplest possible way to find a determinant of a matrix. Okay, like so question comes that what is the simplest possible way, easiest or simplest? Not easiest, because the word easy misguiding. It means that it is not hard working, but it can be some work. But what the simplest possible way to find a determinant? Any ideas, guys? What is the easiest way? Like if you see a matrix, you can immediately see a matrix and say, oh, this is a determinant of that matrix. What is the way out? Like matrix is invertible if and only if the determinant is non-zero, and a matrix is invertible, not invertible, is invertible if and only if the columns are linearly independent, and a matrix is therefore has determinant 0 if and only if the columns are linearly dependent. Now, what do I mean by this? So the question comes, what is linear independence? What is linear non-independence? But do we really need to solve this problem? To know that, we need to understand that. So let me tell you, to save your time. So linear independence means you can linear independence means if summation of, or if you have 5 columns, let's say, if you do this, alpha 1 c1 plus alpha 2 c2 plus alpha 3 c4 plus alpha 5 c5 is equal to 0, it implies that all the alpha I should be 0. Now let's take a simple example to show you, like 1 1 1 3. This is linear dependent, so the columns are 1 1 and 1 3. So if you do alpha 1 plus alpha 2 is equal to 0, you get alpha 1 plus alpha 2 is equal to 0, and you get alpha 1 plus 3 alpha 2 is equal to 0. This is linear independence, and therefore from here you get alpha 3. If you just subtract, you get both alpha 1 and alpha 2 are 0. It's very easy, right? So yeah, this is linear independent. Therefore, this is invertible, and therefore it has determinant non-zero, right? So if that means if all the alpha i's are not 0, that means there is some non-zero alpha I, let's say minus 1, 1, 3, 0, and 5. Some non-zero alpha is a non-zero, right? That means the CIs are independent, are related to each other, are linearly related to each other, dependent on each other, right? Every CI you can write as a linear combination of the other CIs, the columns. So therefore, this is very important to note that I believe the best possible way is that to see whether the columns are dependent or not. So the first step, I believe, is simplest possible way is to check if it has determinant 0 or not. By determinant 0, you have to check essentially its rank or linear independence of the columns, linear dependence of the columns. We have to check if it has determinant 0 or not, right? So let's check it out. Let's see. So observe that, of course, this is not a multiple of the. What does it mean to have to be two columns to be linearly dependent? You can easily see that. Let's observe it very carefully. That if you add this one to this one, you will always get a 0 here, right? So hence, this is not dependent on this two. So what is happening is that in each of them, progressively zeroed as till this point, till all of them actually, till all the four, right? So all the four are linearly independent together. All these four are linearly independent because every single time a zero is added to this third, the next dimension where it is not present in the previous three columns, right? So therefore, no way you can combine them and get the third, fourth one or the next one. So therefore, all these are linearly independent. But what about this? Can we combine this first four, the first four, to get this? Can we combine that? Let's see. Can we really combine the first four to get this? Any idea, guys? Can we combine the first four columns to get this? If not, why? So if you want to combine the first four columns to get this, that means something should be done to make sure the first row is zero. The first one is zero, right? Again, the same thing should be done to check this one is zero. So what do you think? Is it possible? Can you get, yeah, any idea, guys? So alpha 1, alpha 2, alpha. So what we can do is that we can multiply them with alpha 1, alpha 2 to see. So the question is that alpha 1 times 1. So we want to add this 4 with some combination of this 4 to get the last one, right? So of course you can understand that the multiplication with this should be 5 by 2 because in the last one there is no 0. So 5 by 2 should be giving 5 here, right? And if it's 5 by 2, this is 25 by 2 and here is 2. So what should be added? So there should be a constant number, like, so you can solve all of them up till the point and see that no, you cannot do that. So you can progressively solve each of them one over another to get that you cannot solve it. I'm just giving you an idea. Or can you? Let's check it out. So how do you solve this thing? So what if you're asking the question here? One, we're asking that if alpha 1 times 1, 2, 0, 0, 0 plus alpha 2 times 2, 5, 2, 0, 0 plus alpha 3 times 0, 2, 5, 2, 0 plus alpha 4 times 0, 0, 2, 5, 2 is equal to the final one or not. So let me copy this, go to the next page. Okay. So we want this to see that whether it's equal to the final column or not, 0, 0, 0, 2, 5. So we can see it from here right away that alpha 4 must be 5 by 2, right? Because there is nothing else below. So what are the equations did we get? We get alpha 1 plus twice alpha 2 is equal to 0. We get twice alpha 1 plus 5 alpha 2 plus twice alpha 3 is equal to 0. We get twice alpha 2 plus 5 alpha 3 plus 2 alpha 4 is equal to 0. We get twice alpha 3 plus 5 alpha 4 is equal to 2. And we get finally twice alpha 4 is equal to 5. These are the equations we get, right? So from this equation, you can see that alpha 4 must be equal to 5 by 2. And you put alpha 4 here, so you get alpha 3 must be equal to 25 by 2, 2 minus 25 by 2 by 2. So you get this, so minus 21 by 4. And you put it progressively here, and you get alpha 4 and alpha 3, and you put alpha 4, alpha 3 here to get something. Let's simplify it. From above here, you get alpha 1 is equal to minus 2 alpha 2. And you put it here, so you get alpha 2 is equal to minus 2 alpha 3, and you put it here, you get alpha 3 plus twice alpha 4. So alpha 3 is equal to minus 2 alpha 2. But you can see that alpha 3 and alpha 4 are not that relationship. So therefore, there exists no such alpha i's. The only way it can happen is, that means all the columns are independent. Okay, so remember that I didn't do the actual definition, I did it in a different way. If you do the actual definition, the only possible solution will be, because I didn't put alpha 5 here. Okay, so I just wanted to make it's an equivalent definition. So you can understand that there is no non-zero alpha i's that can make this and rank determinant 0. You can say it's a long process. Yes, it's a long process, but once you do, you can easily understand from here that it will not happen. Okay. If you look through it without calculation. And I just took some time to do it. Okay. So we understood that it has determinant non-zero. So therefore, we have to really find the determinant now. Okay. So is there any other way to find the determinant? Is there any other way to find the determinant apart from actually calculating all of this? Any interesting, easier way out to find the determinant? Okay, so what is the next possible way out that is on the mind, that is coming to the mind? That should come to the student's mind. What is the next possible way? That one way is actually trying to do what Indrajit said and actually doing the. So the next possible thing to make it easier is to see symmetry. That's the question. To see symmetry in the. So the next easiest possible thing is to see symmetry. See, I could have just told you the solution, but I don't want to. That's not the way you will learn to think. You should see me think right in front of you. So next easiest possible way is to see the symmetry, right? The symmetry in any the determinant calculation. Can we actually use the original determinant calculation to see any symmetry? Like you multiply with this, and you do with the rest of the aspect, right? Can you see some symmetry out here? So let's try that aspect now. Let's try that thing now. So 1 2 0 0 0, and here it is 2 0 0 0, and there is a matrix here. Okay, let's call it A4. Okay, I'm not naming it. So if you want to find the determinant of this, you see how will you find it? You will find 1 into this one into determinant of A4 minus 2 into determinant of this one. Determinant of whatever 2 0 0 0, and then a submatrix of this one, which we don't know. So let's write it down properly. It's 2520, 2520, 2520, 0252, and 0025. Okay, so this is what we get. That's interesting because it reduces down to us finding the determinant of course for matrix, which is doable. So determinant of this, let's write it down here. So let's look into A4 and this. So A4 is nothing but 5200 200 5200 25200, sorry, 025. This is the matrix A4 and this is the other matrix. So we have to find their determinant. Can we make it easier? Because what is helping us is actually this 0 zeros here. Okay, these 0 zeros are actually helping us. So it's reducing down, it's making the computation less. So let's see what we can get some help from here. In fact, there is a 3 zeros out here, so it's very easy. So what we get here is the following. So we get is 1, so determinant of A4, determinant of this, minus 2 into, you can see again 2 times this one, right? Because it's all 0 zeros here. So 2 times determinant of, so there's another 2 here, so let's call it 2 square. The 2 from this and the 2 from this. So let's see. Let's make it delete, sorry. Let me delete this part and keep it up. Now let's see. So we have got the determinant to be, we have reduced it down to a 3 cross 3 determinant and a 4 cross 4 determinant, which can again reduce it to, it looks easier to do, right? So 5 into this, into determinant of 520 252 025, minus 2 into determinant of 200 252 025, minus 4 into determinant of 520 252 025. So you can see that these two are the same. So beautiful, right? And this reduces down to just 4 and 4, 4 and 5 cancel, so it's reduced down to determinant of 520 252 025, minus 2 is a determinant of 200 252 025. So see, why I did the first method is to show you that the approach should always be finding in the simplest possible way, because this computation is taking a lot of time, right? But this was easier. This was easy to do. See whether it's possible or not. Just solving equations, right? So we always taking the least possible, easiest possible way, unless something grandeur suddenly comes into your mind, right? So now again, it's similar here, right? So it's minus 2 into again 2 here, and then 2 into determinant of this, which is 5 5 2 2, is into 21. And here it's again 5 times 21 minus 2 times 10. So 2 into this one, which is 2 into 5 10. So you get the value 105 minus 20 minus 84, which is 1. So yes, so indeed it was right. But you see the approach here, the approach to what I really want you to understand is the approach. What was my thinking process to solve this problem? You could have actually done it right away, but I didn't do it. But the question is that is there any other way to any other way to find the determinant? Yes, there are multiple ways. The multiple ways is to, I didn't get you. Can you come again? But doing row operations change the determinant, right? You can find the inverse, right? You can find the inverse using row operations, but it changes the determinant unless because you're multiplying constants, right? Non-zero constant. If you swap the columns, that's fine. But you're changing, right? You're doing some linear operations. Like, you see the point that can change the determinant. Did you get it, guys? Okay. So what are the other ways to find the determinant? You can find eigenvalues, right? You can find the eigenvalues and then multiply them, right? That is also one possibility. But eigenvalue can essentially find the eigenvalues equivalent to finding the determinant of another matrix.